I have used this graph analysis tool in countless real-world projects to analyze complex software and in various videos to demonstrate how to perform such an analysis. However, the key to maximizing the value of graph-based analysis is the proper definition of your architecture building blocks. Let's see how to achieve that. What is an architecture building block? It is the unit that is architecturally relevant in your system. This excellent book refers to it as an architecture quantum and defines it as: an architecture quantum is an independently deployable artifact with high functional cohesion, high static coupling, and synchronous dynamic coupling. Before we dive in, the feature of the tool we will discuss next currently supports only .NET. If you want to contribute support for other languages like Java or Rust, here's the project. To analyze dependencies between architecture building blocks caused at the code level due to class dependencies, we open the package dependency graph from the Tools menu. It starts with a basic template. Depending on the system structure, we use different capabilities of the packaging spec to model architecture building blocks efficiently. For a simple modular system where each architecture building block corresponds to a single assembly, we define a single package representing the system and at every assembly we want to include in the analysis. Next, we set the AutoCluster attribute to assembly. This will create one cluster per assembly in the graph. In cases where an architecture building block consists of multiple assemblies, such as front-end and back-end tiers, we define a package per architecture building block, add its respective assemblies, and define a single cluster that includes all types within these assemblies. This results in one cluster per package in the graph. In a microservices architecture or a well-structured vertical slice architecture, the architecture building blocks we want to analyze are often inside assemblies, such as layers of the clean architecture or subfeatures and components within one slice of the vertical slice architecture. To model architecture building blocks in this scenario, we define one package per microservice or vertical slice, add the relevant assemblies, and set the AutoCluster attribute to namespace. The graph will then contain one cluster per namespace. If the previous approach generates too many detailed clusters, because our actual architectural building blocks are defined at a specific namespace depth, we adjust the AutoCluster attribute to root namespace plus n. This groups namespaces at a certain depth level, preventing clusters from becoming overly fragmented due to implementation details. If many architecture building blocks exist within a single assembly, the previous approaches may still not provide meaningful clusters. To improve clustering, we can specify the names of the architecture building blocks in the AutoCluster attribute as a list separated by comma or semicolon. Clusters will then be created for each architecture building block name, containing all types where the full name contains this identifier. Many projects already define their architecture building blocks in configuration files for automated governance using architectural fitness functions. In one of my projects, we use a custom architecture fitness function that categorizes code into features, which should be independent, shared code, which can be used by the features, and composition, which composes the application and can depend on everything. Converting this config into a package spec is a great opportunity to improve our F# skills. This script extracts the namespaces and generates a package spec where each leaf and shared entry becomes a cluster, while composition namespaces are grouped into a single cluster. The composition cluster we usually exclude from our analysis. Reading XML in F# is very easy using the F# data package, which generates parsers automatically based on a sample input. In another project we use NsDepCop, an architectural fitness function that I introduced in this video. NsDepCop defines explicit allow and deny rules between namespaces. This script identifies architecture building blocks from the allowed rules and generates explicit clusters accordingly. These scripts may not fit your exact use case, but they demonstrate how easy it is to pre-process data to fit your needs. For further fine-tuning of our architecture building blocks, we use the cluster editor. Here we can delete predefined clusters, create new clusters, rename clusters, and select classes by pattern and add them to any cluster. Alternatively, we can merge clusters directly in the tree using the context menu or drag and drop. At this point, we have well-defined architecture building blocks and are ready to analyze dependencies using the power of graph theory as demonstrated in these videos.